In this video, I'm going to go over topic 311 about the reciprocal trig functions, which are secant, cosecant, and cotangent. So our three, secant. Secant is equal to the reciprocal of cosine, as long as cosine is not equal to 0. Cosecant is the reciprocal of sine. And kind of one way to remember it, it's the opposite. So S goes with C and C goes with S, if that helps. And then cotangent is the reciprocal of tangent. One thing that's going to make these reciprocals unique is anytime the denominator is 0, our function is going to be undefined there. Graphically, that means we're going to have vertical asymptotes. So secant is going to have vertical asymptotes when cosine is 0. Cosecant is going to have vertical asymptotes when sine is 0. And cotangent is going to have vertical asymptotes when tangent is 0. So first we're looking at the graph of secant. So on here we have the graph of our cosine. And secant is the reciprocal of that cosine. So when our cosine is 0, so at pi over 2, 3 pi over 2, and so on, we have a vertical asymptote. When our trig function, when cosine is 1, the reciprocal would just be 1, so the graph is matching there. As my cosine gets infinitely small, the reciprocal of that gets infinitely big. So we get this graph with kind of these little U-shaped things. So this one has vertical asymptotes starting at pi over 2, because that's where our cosine is 0, plus pi k. So we have a vertical asymptote here every pi units, where k is an integer. Okay. The domain. Okay, the domain is all real values except those vertical asymptotes. The range is kind of a unique range in that this function does not exist between 0 or between -1 and 1. It's just when it's above 1 or equal to 1 or less than -1. So I can write that as from -infinity to -1 inclusive, and then from 1 up to infinity. But we kind of have a dead zone there between 1 and -1. That should be an open parentheses. But this graph does not exist between those values. We have a similar graph for cosecant. Okay, so we have our graph of sine here. Whenever sine is 0, we have a vertical asymptote. Whenever sine is 1, we've got that matching point. So we see a similar idea here. The vertical asymptotes are going to be pi k, where k is an integer, meaning the domain is all of the values except those. Okay, and then it has that same range. There's nothing in between -1 and 1, but from 1 to infinity and from -1 down to -infinity, we have our graph. Next, we have the graph for cotangent. So cotangent is 1 over sine. Since sine is sine over cosine, cotangent is cosine over sine. So just like with cosecant, when sine is 0, that's when we're going to get our vertical asymptotes. So we have vertical asymptotes at 0, pi, and so on. So that's going to be 0 plus pi k, again where k is an integer. Okay, the domain is all values except those. And then our range is going to be all real values, so there's no y value that's excluded. And then one thing I want you to note about this graph is always decreasing. It looks a lot like our tangent graph, but our tangent graph is always increasing unless there's some sort of transformation. Okay, so we're going to let f of x equal 3 secant 2x. Which of the following is a vertical asymptote for the graph of f? There's definitely different ways to handle this. We can take our secant graph. We've got a horizontal dilation of 1/2. What I like to do is look at the reciprocal trig function, which in this case is cosine. Okay, so I'm going to look at the 3 is not going to affect the vertical asymptote, so I'm not going to worry about that. The reciprocal of secant 2x is cosine 2x. So when cosine 2x is 0, this is going to be undefined, and we're going to have a vertical asymptote. So what I'm going to do is graph this. The period of this is going to be 2 pi divided by 2, which is pi. So I've got pi. I'm going to divide that up. So pi over 2, pi over 4, 3 pi over 4. And we're graphing a cosine graph. Cosine starts at the maximum. So there's an infinite number of vertical asymptotes, but anytime this is 0, we're going to have a vertical asymptote. So we're going to have one at pi over 4, 3 pi over 4. Looking at my multiple choice answers, pi over 4 is one of them. Okay. For this one, we want to know where the vertical asymptotes are. Vertical shift is not going to affect the vertical asymptotes. This is not going to, the only thing that's going to affect it is our period here. So I'm going to look at sine of pi x, because when that is 0, our cosecant is undefined. My period here is going to be 2 pi divided by pi. Okay, this one's a sine. So when I graph sine, we're going to start at the midline and go up. Okay, so now we want to pick where these are 0. So it's 0 at 0, which isn't an option. It's 0 at 1, which is an option. So that's going to be our answer. Okay, here. We've got 3 cosecant theta over 2. So which one gives us the range? Okay, this part is not going to affect the range. On my normal graph for cosecant, we know that our graph is above 1 and it's below -1. If I multiply that by 3, that's going to be a vertical dilation. Which we know is going to multiply our y values. So rather than going from 1, but 1 and higher and -1 and lower, it's going to go below -3 and above 3. It's going to pull all those values away from the y-axis or x-axis by a factor of 3. Okay, last one. We've got this guy. Where's our vertical asymptote? So cotangent, again, is the reciprocal of tangent. Tangent is sine over cosine. So cotangent is cosine over sine. So this is going to have vertical asymptotes when sine 2 pi x is equal to 0. So I'll go ahead and graph it again. I get a period of 1. Okay, we have a sine curve. So we'll start at the midline, go up. Okay, so any value there that crosses the x-axis is going to be a vertical asymptote for cotangent. So 0, 1/2, 1 of those, 1/2 is my option. In our last lesson, we solved trig equations. We can do that with not just sine, cosine, and tangent, but we can also solve equations with secant, cosecant, and cotangent. We're going to solve for the trig function, and then I'm going to convert it to what we're more comfortable with, the reciprocal. So here, let f of x equal 4 cosecant x plus 3. G of x is 11. What are the x-coordinates for the points of intersection between 0 and 2 pi? So we're saying, where does 4 cosecant of x plus 3 equal 11? So this starts off nice, easy Algebra 1 style. Subtract 3 and divide by 4. Okay, so cosecant, we're just not as comfortable with that or as familiar with that as we are as its reciprocal, which is sine. Okay, so cosecant is equal to 1 over sine. So I'm looking for where sine of x is equal to 1/2. So between 0 and 2 pi, that's going to be at pi over 6 and 5 pi over 6. Similar question here. Our two equations are 3 minus 1/2 secant x equals 4. We'll do our algebra. Okay, then I'll multiply by a -2. So if secant is equal to -2, we're solving for when cosine equals -1/2. So that's where our x values are -1/2, which is going to be at 2 pi over 3 and 4 pi over 3. Okay, our next equation is a calculator active question. So we're going to look at how we can deal with this on the calculator. So we have p of x is 3 minus 1.7 cotangent 0.5 of x minus 1. And we want to find where that intersects with p of x is 2. So what I'm going to do is I'm going to put p of x in my y1. And I'm going to put 2 in my y2. All right, so I'm going to enter this in. So we've got 3 minus 1.7, and we have cotangent. We don't have a cotangent button on our calculator. We have a sine, a cosine, and a tangent. So we're going to have to use the reciprocal properties. And you have two options. The easier option is to do 1 over tangent, but that gets a little bit dicey because when tangent's undefined, cotangent is defined, so you might have some blips there. So you could do cosine over sine. For this one, since I'm setting it equal to 2, I'm not really worried about those little blips with cosine, or tangent. So I'm just going to do 1 over tangent. So I'm going to go ahead and do an open parentheses. I'm going to use the fraction button because that makes life easier. Instead of cotangent, I'm going to have 1 over the tangent of 0.5x minus 1. Okay, so that 1 over tangent is equivalent to cotangent. In my y2, I'm going to put 2. For my window, I'm interested in where x is between 0 and 2 pi. I'm going to do 0, 2 pi. For my y's, I'm interested in seeing 2, so maybe I'll go from 0 to 5. Okay, as long as 2 is in between there, then we're good to go. Then we'll graph. And the graph will go off the window, and that's okay, because again, we're only interested in 2. Okay, next we'll see our horizontal line. And that's my solution. So I'm going to go to my calc menu, find the intersection. It's going to ask for first curve, enter, second curve, enter. And since there's only one intersection shown, I can go ahead and enter right away. And we have our location. So at 4.0781 is our solution. Now for the AP exam, on a problem like this, since we used the calculator to show our work. What we want to show is what we're doing. So I would write the equation that we were solving. Okay, that would be my setup, and then we use the calculator. This part isn't necessary, but you want to show what it is that you're doing to get to this value. If you just have this without this, you may lose points because it's just kind of a random number. But showing that this is our equation and this is our solution, how we found it was in the calculator, but showing that that was what we were solving. So that was topic 311.